been working in Python for around 8 years, just when I started college. I got into Docker about 1 year ago. This is a pretty fresh technology, so I'm no expert. You should take everything you hear with a grain of salt, because everything I did and I'm going to present, we did experimentally. It's things that worked for us. Hopefully you can learn something. Regarding my background, I did 2 internships at Google way back when I was in college. I used a bit of Python there as well. After that, I worked on a couple of startups. I actually worked right here in this building at Cluj Hub. The first one was Used Together, and it didn't work out, so we started another project called Rently. Both of these are Django apps built with Python. And this brings us to where we are today, which is Reps. It's a company I co-founded. A couple of my coworkers are here as well, Katalin and Spir in the back. You should go say hi to them if you can, they're really cool people. Yeah, so this is actually a spin-off, a pivot of the Rently project, which did not work out. We are a company focused on building software as a service platforms for real estate professionals. We're a small startup, we're all young and talented, and yeah, we have really big plans. This is our product, which I'm going to talk about. It's a CRM, as I said, built for specifically for the real estate niche, for agents and managers to manage their whole business. It's entirely built on Django, and as of almost 1 year now, I think, we are running 100% on Docker. Okay. I'm going to go through a quick history of how our infrastructure looked like and how we evolved over time. This is a Fabric script. I'm not sure how many of you are acquainted to Fabric. Basically, this is a script that runs on a remote host via SSH. We were running on a single server back then. It does basic stuff that a Django app needs. It simply SSH onto a remote server, did a git pull, install all the requirements via pip, and then do the basic stuff needed for deployment, compile all the static assets, compress everything, do database migration, and then simply restart all the servers. It was all really simple back then. And then, we started getting a bit more serious. We started the need for more servers. We had to scale horizontally. So this didn't cut it. This involved a lot of manual intervention. We were still fiddling around with config files and getting all sorts of dependencies, and that's not really good. So we tried SaltStack. SaltStack is a configuration management tool. It's very similar to Chef or Puppet. You probably heard of those. Those are the more popular alternatives. I'm just showcasing here a bit of how a SaltStack configuration looks like. This is actually a state that we want our applications to be in. For example, this tells Salt to just get the latest git pull based on a number of parameters that are stored in Pillar. Pillar was this distributed key value, global configuration. It all worked out pretty okay. We managed to scale our infrastructure, go to different servers. It was the first time that we could actually deploy configuration and not, SSHing into servers and doing all that dangerous manual editing of configuration files. But this quickly turned a bit overwhelming. Soon enough we migrated our whole infrastructure. We had like 4,000 lines of configuration, just as you saw in the earlier slide. This is actually Jinja 2 templating over configuration files. So this is a really simple example, but trust me, there were also configuration files that were really unreadable. So at one point I had to explain how SaltStack and the whole infrastructure management worked to a colleague of mine, and I realized that they needed to read like 20 pages of documentation. So yeah, we find that it's also kind of hard to scale. It wasn't easy. You still had to manage a lot of stuff and do a lot of configuration aside from SaltStack. Like we didn't have automatic service discovery, for example, or load balancing. We had to build around it a lot. And yeah, also I find it's really ugly and unmaintainable. So we started looking for alternatives, and we were facing other problems as well, like scaling. If we wanted to add more servers to our fleet, for example, we still had to fiddle around with configuration. We had to tell the system, what goes where and how do they all connect to each other. Redundancy was also not managed out of the box. If one of our servers went down, there was no self-healing or self-balancing. And yeah, flexibility is related to these two. If we add a new server, we still had a lot of work to do. So yeah, that's when we tried looking at Docker. Like Docker had this promise of solving all these problems. How many of you have worked with Docker before or know how it works, more or less? Right. So not that many. Basically, Docker has this promise of, in layman terms, like running real lightweight virtual machines, right? So you build Docker images, that's how they call it, which then get deployed and run on a server, and they're totally isolated from each other, but they use common parts to save resources. So what I have here is an example of a very simple Docker file. This is used to basically compile a Docker image for a Django application. I'm going to explain it line by line. This is a base image used for Docker. It's based on Ubuntu Xamarin. The build pack depth means it comes pre-configured with a lot of tools used for compiling and installing stuff. Basically stuff like build essential, GS, CC, Git, and whatever.
Okay, so you won't need to run the commands to install some extra.
Yeah, basically, yeah, those are already compiled in the base image. Mm-hmm. And what happens if each time you run a command like this one, it builds upon layer by layer. Okay. So you have a bunch of dependencies installed right here. You then run another command. It adds it's actually a file system layer that's used by the image with all other sorts of dependencies that you need for application. For example, here we're installing Python pip, and this is a really long list that I have not included, but it's not relevant. But basically, these are mostly dependencies that are needed to install pip packages. So after we install their dependencies in pip, then we install pip itself, and then install our Django application requirements via pip. And this is the actual application code. Then we run a manage command which compiles the translation file. This also gets added to the base Docker image. And these last two lines, this tell the Docker image that, hey, this is a Docker image that exposes a service on port 8000. So other services can later connect to this port, to make your application work. We'll get to that. And this is the command that this is the entry point basically for the Docker image. So this is a shell script that runs the Django app on port 8000. All right. So Docker had this promise of building really compact small images that you can reuse and distribute really easily on multiple machines. The problem was how this all fit together. Okay, at that time, this was a year ago. It does not seem like much, but Docker has evolved tremendously over the last year. Back then, there were no things like built-in orchestration or multi-host networking. Okay, so this was actually a really hard job to make it all come together. Fortunately, there was this startup called Tutum, and they built this product. It was called Tutum. It was acquired by Docker. Now it's called Docker Cloud. It's a containers as a service platform. So what it does is offer all these features for you: orchestration, multi-host networking, and volume management. This allows you to just define bits of architecture from your stack. You have a web worker, a database, a front-end server, and Docker simply allows you to link them all together over multiple servers and just run them as a full stack. It abstracts all the details of how they're connected to each other. I'm gonna talk about the terminology from Docker Cloud a bit. Nodes are machines that run your Docker containers. You can assign tags to them. These are useful for orchestration. For example, you can tag your servers with, say, this one has SSDs. I can use this for I/O heavy workloads. This one has high memory, and so on and so forth. Docker Cloud Stack defines how like an application with multiple containers, multiple Docker images will talk to each other and how they interact. The Docker Cloud Stack file syntax is very similar to Fig and Docker Compose. You might have heard of those. Actually, both were inspired by Fig. And a stack is made up of multiple services that are linked to each other. So multiple services form a stack, and a service can contain multiple containers. Containers are, imagine like processes forked running the same thing, but they can be over multiple machines. So this is an example of a stack. This is actually how our current web application runs right now. This is the stack file. It's highly simplified, but it showcases the most important parts. This is a YAML file that describes each service in particular. So, for example, we have here, these are our 4 main data backends. There are Memcache, Postgres, RabbitMQ, and Redis. I'll go back line by line and explain what each line means. So this is the service name. Okay. Each service contains an image. This is the image name. They are stored in a Docker Hub. Basically, this is what a Docker file that I have shown earlier compiles into. It has a name and a tag, which is a version similar to how Git works. This is the command that the service runs based on the image. Restart always means, hey, if this thing crashes, please restart. This is really important. Note it down. And these are our tags that tell the Docker Cloud orchestration system which nodes to deploy to. So this Memcache service will only run on nodes that have high memory, for example. Same with Postgres. You can define environment variables for your services. We use this a lot to control the behavior of the services and inject a lot of stuff like access keys and how this service should behave. So we have 4 data backend services defined, and then we'll get to this is the Django application image, right? This image was actually the one that I showed earlier, the Docker file, which compiles into this image and is pushed to a Docker registry called the Docker Hub. This image is linked to all these is for backend services. So what this means is that each service gets an alias, Memcache, Postgres, RabbitMQ, and Redis, and they can simply connect to this service no matter where they are in the node cluster. Okay, so that's the multi-host networking architecture that Docker Cloud promises. No matter where you run, you can connect to this.
Yeah, I have some question.
Yes.
On the deployment strategy, what does high availability mean?
Okay. So Docker Cloud offers 3 deployment strategies. That's how they call it. They are emptiest nodes, what's it called, high availability, and every node. When you deploy a service, you can tell the orchestrator what strategy to use, basically where to put the service on the available nodes. So high availability means you should distribute this service on as many servers as possible. Okay, here we have on this service 5 containers running, right? So if I have a fleet of 5 servers and I use the high availability deployment strategy, it will guarantee that there will be exactly 1 container in each of the servers. So this is in case server crashes, you always have redundancy on one of the others.
And the other deployment strategies were
I'm not sure. They're here somewhere. All right. Emptiest nodes means deployed to the
Least load.
Yeah, the least loaded server, basically where you have the most spare capacity, high availability, and this is a special node called every node. Basically, if you add a server to the cluster of servers, it will automatically deploy that server on every server.
I see. And how is that different than high availability?
Because every node means that there are exactly as many containers as the number of servers. In high availability mode, you define the number of services, the containers you want running, and then it will automatically, distribute it.
Yes, you don't give a number.
Yes.
It means, yeah, I get it.
Yes, question there in the back?
So do you have a load balancer compiler for the application?
Yes, I'll get to that later. It's in the presentation. We'll get to that.
And in the links, you have the service name, and the other part is the port, or what is it?
No, so this is the service name, and this is an alias. So
it's a host name.
yes, it's exactly like a host name. I'll explain later. It works as both a service discovery mechanism and a load balancer. The useful thing about these aliases is that you can have multiple stacks. For example, this is a production stack. It's a CRM rep, prod, Memcache, and it's linked with the name Memcache. I could have a staging environment which would be linked with a different service name, but would have the same alias. So then the application doesn't know in what environment it's running. It only knows that, hey, I can connect to a thing called Memcache. I don't know who it is or what it's running, but I can use that.
And the sequential deployment.
I'll get to that later. I'll explain that later. Sure.
So I assume you have more than 1 container running Memcache, right?
No. It's one. In this case, it's one container in the service per stack.
Okay, so all entries in links section, each entry is one container, linked to 1 container.
In this case, yes. There can be more, but in this particular case, yes. I'll also get to that later when we get to load balancing. Okay, here I'm showcasing other types of services that we're running. These are all based on the same Django application image, but they're doing different stuff. So the one before was the Django web application. It uses the same image, but it has a command overridden, which means that the Docker container will run a different command when it's running. So for example, this one runs an API web interface. This one runs a salary worker. They're all based on the same image, but they're running different commands to accomplish different purposes. They all have the same links here, and we can control a different number of containers for each of them. For example, here we have a salary workers, which are our background tasks, workers that are consuming different queues. Here I'm showcasing a queue named batch and a queue named priority. The nice thing about this is that we can control the number of containers independently for each type of queue. So if we have, say, a workload for background tasks, which fluctuates greatly during the day, for example, we can control the number of containers dynamically for each kind of queue. All right, I'm going to explain a bit how this this multi-host networking works. So back in the day, you know, in the early Docker days, you could do the service links like I've showcased before, but they would only work in the same machine. You could only link Docker containers running on the same machine. Docker Cloud introduced this, uses actually this service called Weave, which was basically running a Weave agent on each of the servers that were running Docker containers, and it would create a virtual network and assign a virtual IP to each of the container, which could then talk to each other. So this was only between all the Docker containers running on the host. Right now, in the latest Docker versions, namely version 1.12, which is the newest, they've introduced this concept of network drivers, and it's a plugin-based architecture. So now Docker offers this overlay networking, how they call it, built in out of the box. Docker Cloud doesn't use that; it still uses Weave. It's another version of Docker, but I'm assuming that they're going to switch to this. Okay, so let's talk about service discovery. As I've shown before, you can assign aliases to service links. Okay. What happens is if you try to connect using a DNS name, it will act as both service discovery. It will give you the IP of all the Docker containers running that service, and it will also do load balancing. Load balancing via DNS round robin. The way we do load balancing for our application, for the web application, it's using a custom HA proxy provided by Docker Cloud. I'll showcase in the next slide how to use this. Basically, you link all your services that are web-facing to this image using Docker Cloud/HA proxy. And this uses the Docker Cloud API to discover all your services and load balance among them. So, for example, this is the HA proxy running on the servers. The ports here part is important. 80 to 80 means you should bind the server's 80 port to the container's 80 port. So every request coming from the internet, from the outside to the server's 80 port, will get into the HA proxy container image. So this is the only image that we use that is accessible from outside the server. What this does is then it redistributes the traffic to all the Docker services that are linked here. And the way it does this is based on domains that are injected in the front-end services environment. So, for example, this is kind of a strange link because it's in a different stack than the HS proxy is running. So this means link the CRM reps prod web service for the CRM reps prod stack with the name CRM prod web. And then it looks at this image that's in a different stack, and these are some special magic environment variables. Linked services can read each other's environment variables. So basically this tells the HA proxy image that, hey, any request that you get that matches these domain names, crmreps.com and .ro, you should load balance to this service, okay? So in the example before, I showcased that this service is running 5 containers, right? And the HA proxy will just forward a request to this DNS name. This DNS name will resolve to any of the 5 IPs that the Docker service is running. So it will load balance via round robin to each of the 5 services. And same thing with the API. You have a different virtual host. So you can have a lot of services run here. We have a lot of services on our HA proxy, and they are all served by a single front-end image. Okay, how does deploying work on Docker? When I mentioned the early Fabric file, you know that there are a lot of stuff to do when you do a deployment. You have to compile static assets, do database migrations. You know, with Docker, it's really easy to just build an image, push it to the repository, and restart the service. You know, you would get the latest version of the code right away. So what we needed here was a way to run this custom script that would do all the deployment steps that are required for deployment. So we built a special image which we call deploy that was linked to all the backend services, just like the Django application. And then we would run this container. It would do a one-off job, which was basically just these steps. You know, migrate the database, build the static assets, and then it would shut off. After this Docker container would shut off, we would then restart the web containers. Here's where the sequential deployment option here is important. So we have 5 Docker containers running in high availability mode with sequential deployment. What this means is when the service is restarted, Docker Cloud would shut off and restart all the containers one by one. This way, you know, you restart one container with a new version, it gets pulled out of the load balancer, it restarts, gets added back right to the load balancer, and then the next container restarted, and so on. So what happens is you have a gradual rollout of the deployment across all the servers. All right. After we got this dialed out, you know, we started wanting to automate this whole deployment scheme and infrastructure using Jenkins. We started by first running all the test jobs in Jenkins as Docker containers. That was pretty straightforward. We started building the Docker images in Jenkins. What this means, just a simple git pull. You build the image and then push it to the Docker registry, the Docker hub. And then we build a custom deployer, which is the deploy job, which would update the Docker Cloud Stack using the latest configuration. This is stored in a repository. It would run the one-off deploy container, which I showcased earlier, and then restart all the web and work containers. So this is all that it takes to do a deploy. It's fully automated using Jenkins and Docker. And then comes the issue, you know, we wanted to move our whole infrastructure on Docker, not only the Django applications, we want to also run Jenkins on Docker. And that posed some interesting challenges because we were using Docker to run Jenkins, but then we would have Jenkins jobs inside Docker, which would use Docker to, you know, build and deploy. Yeah, so yeah, this is the Dockerception problem. And there's 2 ways to do this. One is, it's called Docker in Docker. It's a special Docker build which is able to run inside Docker, but apparently there's a whole bunch of problems with that because you're using a layered file system, and then when you try to build using Docker inside the Docker image, you get another layered file system inside, and apparently, you know, some combinations are really fucked up and just the curatorial files and everything burns. I'm not sure how this all works. People smarter than me said, don't do it. So yeah, the solution is to link your Docker socket and binary from inside the Docker container to that of your host. So what happens is when you're inside the Jenkins container and you issue a Docker command, it will actually proxy it to the Docker command, to the Docker daemon running on the host. So if you do a Docker build inside Jenkins, it's not going to build the image inside of the Jenkins container, but it will build it on the host. Okay. This has an advantage of using the host Docker cache. Basically, if you build an image and later on you try to pull it from the repository, it's already there because the host built it, not the Jenkins container image. So this is how it looks. It's an image running Jenkins, and you bind the Docker binary and the Docker socket running on the host to those running on the container. So this is really all it takes. Every Docker command that you issue on your Jenkins master or slave, we're using both Jenkins slaves and master, we'll just use the host. Yeah, another advantage is that we are also running the Jenkins slaves in Docker, so we can really easily scale them horizontally. With just 2 clicks, we get how many Jenkins slaves we want. So yeah, that's good. And then up to this point we were simply running production and staging environments like in our old infrastructure. And one of the reasons we moved to Docker is we want to really easily, bring up multiple environments very, very easily. So all you have to do if you have a production and staging environment, and you want to clone them to test a new feature, for example, you can simply just almost copy paste that stack file, the stack configuration, and tell Docker Cloud, hey, bring me up a new infrastructure. It will automatically distribute all the services in the cluster. So what we ended up doing is just have a simple configuration like this, and we can just in a simple YAML file, similar to how a stack file works, we can define stacks which are based on the same stack configuration, running database backends, web workers, API workers, salary workers. And we just like in seconds we could run across the whole infrastructure a whole new stack started from scratch. So this is really important because it abstracts the whole orchestration stuff. We don't need to think how many servers do we need. If there's spare resources, the Docker Cloud will just use them. If you run out of resources, we add a balance. So we can run easily as many environments as we want without adding servers, so long as we have the spare capacity. Okay, so then we get to monitoring. Obviously, we want to run fully on Docker, so we started using Docker to monitor Docker. We run InfluxDB, Telegraph, and Grafana stack. InfluxDB is a time series database. It basically stores any time series information you want. This data is provided by Telegraph. Telegraph is a new data collection service. It's similar to maybe how StatsD or CollectD works. It takes a bunch of inputs, which it could either read from the system, receive from other services, and it would write them to InfluxDB. This works in the same way as a Graphite backend works. Maybe you're more familiar with that.
So this supports the Docker logging system as a backend? Yes.
Telegraph supports a lot of plugins, one of them being Docker, so you can get information about all the Docker containers running on a server. Grafana is The visualizer, it uses the data stored in InfluxDB, which is provided by Telegraph. So the way Telegraph works, it basically pulls data from a bunch of sources that you can define and then writes them to InfluxDB. We have a master Telegraph service, which basically just receives information, aggregates it, and then writes it to InfluxDB. And then we run a Telegraph host service, that's how we call it, which is run on every host. This is important. Remember when I was talking about the every node deployment strategy. So in this case, this is really useful because every time we add a server to our fleet, this Telegraph host service will automatically run on that server. And this is configured to monitor the host health and also gather information about all the running Docker containers on that server. So what this means is that every time we add or remove a server or add new Docker services or stacks, this will automatically get monitored via this Telegraph service. And then if you want to do some extra monitoring, we could just point our containers directly to the master Telegraph container. For example, in our Django applications, we monitor things like page hits and timings, and these are sent directly to the Telegraph. So this is how the master Telegraph service looks like. It's connected to the backend services. It pulls them for data and then writes it to InfluxDB. And this is how the Telegraph host service looks like. It's got a bunch of volume mounts here. These are used to monitor the system health, and also it is used to query the running Docker containers and how many resources they use, and so on. As an example here for our web service, this is linked directly to the Telegraph service, which it uses to send stats about how the app is working, timing, request timings, and so on. And this is just a glimpse of how it would all look like. This is stats about running servers and containers. Just as I said, via the Telegraph host service, every container or server that we add will automatically get stored in here.
Do you have anything nice to see log messages? See the logging messages. Yeah,
logging. So yeah, we use we externalize this component. We use log entries, but it works in the same way. There's a log entries agent that is run with every node strategy. So yeah, same thing happens. It just pulls log information from all the running Docker containers and aggregates them. So logging and monitoring, yeah, they're really working the same way. Just deploy a service to every node and it gets all the information it needs. All right, so what does the future look like? Docker recently introduced in version 1.12 a new Docker Swarm. This is basically all that I've presented here in Docker Cloud is now, it works out of the box in Docker, it's batteries included. It supports orchestration, a built-in overlay network. It doesn't need that Weave plugin that I've mentioned before, which was not available. And it's now built on a plugin-based architecture, meaning that third parties can implement stuff like network drivers. You can do all sorts of fancy stuff. The overlay network is what Docker Cloud is using right now, and it works great. The interesting parts are volume plugins. The one limitation that Docker Cloud has right now is that if you define a volume on a Docker container, it will get stored on the host. This is used for containers with persistent data, like databases. Web workers, for example, don't need volumes because they're ephemeral. They're just run off. You can restart them. They're stateless. There's no things to be stored. The problem with volumes is that once you start a container on a server, its volume is stuck there. You can't move it. You can't move that container to another host because it will lose all its volumes or its files. So Docker's plan to solve this is by using volume plugins, which lets third parties manage how data is stored. The Flutter plugin, for example, it's kind of similar to what the overlay did for networking. Flutter does for volumes. It runs a Flutter agent on each of your nodes, and you can define a volume to use the Flutter driver, and it allows you to move volumes from one host to another. So if you want to decommission a server or move one service from a server to another, Flutter will automatically move the data with it. Convoy is another example of a volume plugin that's really useful. It can do snapshots, backups, restore, and a whole bunch of different online services. So it's important just to not lose your data stored in your volumes. And I think this is it. Do you have any questions?
How do you do development? Do you use Docker Compose or
On local machines.
On local machines. We don't use Docker on local machines yet. We plan to do that. Yes, we're gonna use Docker Compose. We're gonna use Docker Compose. That we have prototypes working, but our whole development workflow was based on not using Docker yet. So we're gonna do that.
And on the testing slides, did you try to use anything else besides Jenkins, like GitLab, CI? Have you looked at that?
No, we didn't really have any reason to use anything else. It's just a simple build a container and run the test.
Mm-hmm. And the tests they run in container or?
Yes, they run in containers, inside a container. So it's basically it's the same container that is used in production, but it's given a different test command.
I see. And did you try to look at Kubernetes as a replacement? Since you're looking at Swarm, you might as well look at Kubernetes.
Yes, as a matter of fact, I did look at it. I don't know. I find it way too complicated at first sight. So, I don't want to go there.
You mentioned that this distributes to how many servers you have. So you have this server set and it distributes server. Is
Yes.
there a way to specify that this one node should only run this service?
Yes, you can do that by tags. So you can specify a number of tags on each server, and then you can put tag requirements on service. So this service needs to run on a host that has these specific tags. So this way you can control where the service runs.
You explained how our request is handled once it gets to HA proxy.
Yes.
But how does it get handled before that? Do you have multiple instances of HA proxy or?
Let me get back to the slide.
So coming from the outside world, how does it get passed on to the actual machines?
Okay, so this is basically, its port is bound to the server's port, so you can just point your DNS to the server's ID, for example. Docker Cloud offers another feature, which is like an external DNS name for the service. So Docker Cloud would give you a huge ass domain name, a hashed domain name, for example, which will always point to this specific service. Mm-hmm. So if you, for example, scale this up or down, run more containers on it, that external DNS name will automatically update with the IPs of all the servers that is running the container.
Okay, so it kind of does
so you
the
can
same thing, but on the external
Yes,
side.
on the external side. So you could have your domain with a CNAME pointing to the Docker Cloud DNS name.
Mm-hmm.
So yeah, so this scales both inside Docker Cloud and outside of it.
Does the Docker Cloud support what was it about to ask? Health checks?
Well, it does support health check at the application level, for example. This is HA proxy health check right here. So this is at the application level. Hey, do a check at 2 seconds each.
So you have to do it on your phone, practically.
Yes.
Because the interesting thing about Kubernetes is that it has built-in health checks and also has rolling restarts. It has
definitely Kubernetes is a much bigger monster. It's way more mature, but
the configuration is a bit more involved.
What were the downsides to moving to Docker? Did you have any pain points along the way?
Well, not really. To be honest, this was the simplest migration that we did. For example, when we started out with SaltStack, that took a shit ton of time, and we ran into a bunch of problems. The transition to Docker was pretty smooth. My only complaint was that Docker Cloud itself, the platform, it's a bit quirky. It does fail sometimes. The API calls do tend to fail every now and then. Just retry it and it works.
Have you tried restarting it?
Yeah.
We didn't have some DNS issues at some point.
So the biggest pain point with Docker Cloud was the DNS. It kept failing every now and then. This is precisely the reason why we don't use this whole external DNS mechanism that I pointed out, specifically because it failed like a couple of times for like half an hour or something. Our whole service is down, so now we just point them to the IPs. So we saw that. But it seems to be getting better right now.
And I'm guessing the internal DNS is way more reliable.
Yes.
So you're renting dedicated servers, and Docker Cloud, it's something that runs Docker. It's a software as a service.
Yes, it's a software. They call it containers as a service. So what happens is you run your own servers and install a Docker Cloud agent on each of the servers, and that communicates with the Docker Cloud APIs and does the whole orchestration thing.
Can you scale PostgreSQL horizontally and memcached as well?
Yes. Yes, it's not showcased here, but we do that. We do replication by Docker links, and
did you have the master setup or like failover?
No, master slave with failover. Failover is currently handled manually.
So you can scale reads, but you can't scale writes. That means if you have a single container that is master.
Yes, that's right. There are mechanisms for scaling out with write horizontally.
And
it seems way too early for that.
That new distributed volume stuff that probably adds latency and stuff like that. So
the way that works is the volumes are stored locally on the machine that runs the container. But you can move the container to a different machine, and then the volume moves with it. Okay, so it's always right into a local machine, but you can move it.
Okay, so it's not synced live.
No. Although there is, so I've talked about it supports volume plugins, so there probably are plugins that do this. I probably wouldn't recommend it, but I'm sure it's possible.
So I guess state would be better probably saved in modern tools like NoSQL databases, which are by design distributed, and object storage, things like that.
Yes, well, that depends on the application and what the requirements are, but
it's an ongoing debate.
Yeah. I mean, there probably are volume plugins to use stuff like Amazon EBS, for example. You can probably do that and kind of solves half the problem, I guess.
How about security? So you are in your isolated environment. You control all the dedicated servers.
Yes.
You also probably have an isolated layer 2 network. I don't know if your network interferes with other tenants from that data center.
No, it's our specific network is isolated, so we don't bother with that.
So
The Docker Swarm, for example, I don't know much about it. We haven't just read a bit. They do some fancy security stuff, totally automatic. They use TLS handshaking with rotating keys, and it's all done automatically. You don't have to configure anything. So if you're using Docker Swarm, all your traffic is encrypted. So there's no worries there.
one of the original problems of Docker was security, assuming you are running multiple tenants on the same physical machine. So two containers on the same machine are owned by different companies, let's say. So there were some exploits that you could get out of the container and get on the host. The problem
I wouldn't run a container on a server which I don't own, so I don't know.
More questions?